Since 2009, Sapienza Flight Team is a student research project supported by University of Rome La Sapienza. This year, the development team counts 35 bachelor and master degree students from various departments of Sapienza University, including aerospace, electrical and control engineering, physics and mathematics, artificial intelligence and management, divided into 6 divisions. The team started a long-term project in 2016 focused on the development of a custom-made autopilot, which has led to the publication of various articles and theses. The project aim was to participate in Suas using our own autopilot instead of a commercial one. Due to the complexity of this task, during the years the team faced various technical challenges that never allowed us to attend the competition. Furthermore, last year during the parachute drop test we experienced a major crash in March that destroyed our only aircraft. We were on the verge of giving up, since we couldn't test and fine-tune the autopilot and computer vision system, but we managed to build a new aircraft in the shortest time. Afterwards, we spent an immense amount of time at the airfield, conducting extensive flight tests almost every day for a month and a half. This deepened our understanding of the entire system and allowed us to achieve our dream to see our autopilot fly for the first time and to bring our aircraft to the 2023 Suas edition. P8-NB8 was specifically designed to compete in Suas 2024. After analyzing this year's rules, we made a strategic decision to drop all 5 bottles in a single flight, in order to optimize our timeline score while maximizing the aircraft's 38 minutes range. P8-NB8 has a flight range of 22 miles at fully loaded weight, which is 32.1 pounds, thanks to two 5S 16,000 mAh lithium battery propulsion packs connected in series. It's able to perform agile maneuvers with a turn radius of less than 70 feet at a cruise speed of 48 knots, and to take off and land on a 130 feet runway. The UAV is capable of accomplishing a set of missions by keeping high safety and reliability levels, as well as high-precision autonomous flight. A multidisciplinary optimization approach was necessary to complete the system design, based on time and budget constraints, team experience, workforce, and available means. After last year's challenging experience, we are raising the bar by refining our design and tackling the weaknesses exposed by last year's inexperience and time constraints. The new aircraft is focused on efficiency and reliability, and we took major focus on refining and working on the reliability of the ODLC hardware and algorithms. P8-NB8, in Italian P8-NB8, is a high-wing electric propeller engine aircraft, driven by a team-developed autopilot installed on an onboard computer designed and tailored specifically for the team's autopilot. A Jetson computer is used for the AI for the ODLC. A line communication between the autopilot and the AI allows the airdrop mechanism to correctly spot and reach the ground targets with the payloads.
The image acquisition setup is a Basler AC2 industrial camera with an EMX542 global shutter sensor, which can shoot at 23 fps with 16.1 megapixel resolution with a 60mm non-distortional lens, ensuring high color accuracy. After some trials, we decided to shoot at approximately 120 feet altitude to maximize the capture area and at the same time guarantee the best recognition performance. Our UAV mounts an NVIDIA Jetson Orin AGX, making the ODLC system run smoothly and efficiently thanks to its 64GB of video memory and powerful GPU. The ODLC process consists of several steps coexisting in a general pipeline coordinating the various processes. Compared to last year, this year's code base was focused on modularity and concurrency. A number of multiprocessing capabilities and dynamic, object-oriented code practices were used to ensure maximum utilization of our available hardware resources, together with the possibilities to hot swap different AI models for quick prototyping. The pipeline is divided into 3 sections. Picture gathering. Picture are captured using proprietary Basler camera software. They are then inserted into multiprocessing queues as NumPy arrays to be consumed by later pipeline sections. An interference system. For the target detection stage, several models were considered, including YOLO-NAS, YOLO-VAL, and YOLO-VAM. Every model was trained on a train validation test split of the original dataset, including over 40,000 real images shot in different light conditions using both multi-capture and the fixed-wing aircraft itself. Another 50,000 images come from a synthetic dataset realized in Blender to reproduce the competition airfield in the closest way possible. YOLO-NAS attempts to detect all features at the same time, while the YOLO-V8 large and medium variants are employed as part of an ensemble of 3 different models. Each one is responsible for the detection of a separate feature, shape, color, and character. Even though it seems less convenient from a computational point of view, this choice actually increases scalability in the model by reducing the number of total classes, resulting in a more dense dataset overall. Specifically, shapes are detected by YOLO-V8. The resulting patches are then fed to YOLO models for color detection, and to a fine-tuned EfficientNet S classifier for character detection. Decision system observes target recognition. The decision system steps into determining the actual drop locations of the payloads. The confidence level extracted from YOLO combined with information about the flight targets that are communicated at the flight line help the decision system to refine the detected targets into more confident predictions. Geolocation by energy accurately determines the location of the target by recovering the perspective protection of the aerial photograph. This process requires considering variables such as the position, attitude, and altitude of the UAV and the positions of the camera's focus relative to it. As a result of numerous tests, the team observed that thanks to the chosen optics, lens deformation is not significant compared to measurement errors. In addition, Geolocation provides estimates of measurement errors, exploiting methodologies such as Monte Carlo and maximum likelihood estimations. These techniques allow us to compare elliptical confidence regions built on each sample of the same target. Tests validate the mathematical model by confirming an empirical error within 16 inches. Thanks to the accuracy and robustness of our system, no additional operators are used for the ODLC tasks. All the process is fully autonomous. The fuselage has been designed to carry on the inside all the 5 payloads in one single flight, and the release mechanism is managed directly by the onboard computer. Dropping point. To ensure accurate payload release, we rely on a 6 degrees of freedom effective mathematical model that integrates lateral and vertical drag coefficients, considering wind and cylindrical symmetry of the payload. The release point is determined by statistical simulations, taking into account the landing error, ensuring maximum accuracy and mission execution. The jet zone calculates the airdrop coordinates, direction, and speed, and sends them to the autopilot as an additional series of waypoints for the mission. We tested our model by performing static and in-flight drops during the year, and analyzing data from 146 launches, we evaluated the impact of wind on the average landing error. Comparing it with different parachute openings altitudes, we observe a correlation between the data. The payload. Hardware-wise, the payload system includes a lightweight and easy-to-remove structure that houses the bottle, a safeguard, a latch on the side for the parachute, and compact onboard electronics, which include a barometric sensor and an AT-Tiny85 microcontroller that manages the parachute release. The chip-run software coordinates the payload through 3 phases: standby, activation, and execution. During the first one, the payload is inside the UAV, and the safeguard is attached to it. When the safeguard is removed using a servo on the aircraft by a command on the autopilot, the AT-Tiny85 enters the activation phase and monitors the altitude through the barometric sensor. When the predetermined altitude is reached, the microcontroller goes into the execution phase and activates the latch for control release of the parachute, ensuring precise and secure control during transport and release of the payload. This mechanism dramatically increases the drop precision with average wind at an altitude of 115 feet. The estimated average landing error is about 23 feet, while releasing the parachute at 15 feet, the error reduces to 12 feet, safely inside the acceptance radius.
Communication system between UAV and ground control station consists of 2 RFD900X US modules with a 3 dBi omnidirectional antenna on the drone and a custom 10 dBi Yagi antenna on the ground, mounted on a fixed tripod near the GCS. For redundancy, there is a second link via Futaba 2.4 GHz S-bus protocol receiver that connects the drone to the remote controller and the GCS, manned by the safety pilot. This is activated in case of critical failures of the autopilot system. The ground station consists of 1 laptop and a radio modem. Communication with the autopilot is based on the MAVLink protocol. The front-end interface is a modified version of Q ground control that displays mission plans and boundaries, performs telemetry, and transmits command and control messages. The use of RFD900X US modules assures a continuous, reliable, and constant daddling during the entire length of the mission, tested for twice the competition maximum distance. Furthermore, they are FAA standards compliant. All the tests for the antenna performances were carried out at our airfield in situations similar to those of the competition, with other UAVs flying with various frequencies. The used evaluation metrics are the RSSI, Received Signal Strength Indicator, and the number of received packets. Both of them can be measured using the RFD Tools software. Different trials have been made with different values of data rates, transmitted power, and distances. Communication to the Jetson during setup time is done through a 2.4 GHz link directly to a computer. In addition, a 2.4 GHz FAA ID sender telemetry is installed on the aircraft to comply with US regulations. In case of emergency, the safety pilot uses a Futaba radio controller, which guarantees seamless and continuous communication. Following last year's development and thanks to new rules including smaller bottles, the challenge was to improve the aircraft's performance and maneuverability. The new P8-NB8 aircraft is based on a similar design concept as the previous INEA aircraft, but is equipped with a fuselage made with composite materials, which dramatically increase aerodynamic efficiency and reduces its weight, keeping it spacious at the same time, thanks to careful cable management and better spaces allocation. In addition, after CFD optimizations, the tailplane has been completely revised. P8-NB8 is a fixed-wing aircraft developed along a main carbon fiber boom. This configuration allows agility in disassembling and assembling operations and guarantees good modularity and easy replacement of damaged components. The aircraft is propelled by an Agar A60 electric motor mounting a 21 by 13 WE APC propeller. The fuselage is designed to maximize space optimization, achieving convenience in accessing electronics for maintenance and quick battery replacement, reducing setup time. The front nosepiece houses the ODLC equipment, while the rear is dedicated to payload release. The undercarriage system is configured with a front wheel and a rear main landing gear in order to implement the autonomous takeoff and landing, since a tail-dragger configuration is too difficult to land by an autopilot. To improve aerodynamic performances, the fuselage section area was minimized and the main boom was incorporated inside the fuselage. Wings are attached to the main boom with a bayonet fitting mechanism, and their support is 3D printed using carbon fiber reinforced PA. new fuselage design incorporates a telescopic tube as its primary structural element, facilitating easy disassembling by allowing the boom to slide within it. Composite ribs with a plywood core coated in carbon fiber maintain the fuselage in shape, while the fuselage coverage consists of composite material with 2 layers of carbon fiber. The molding process has been carried out using 2 semi-molds created by a resin 3D printer. Accessibility of this system is ensured through a series of hatches cut into the fuselage, which also allow payload dropping. 5 hatches, each equipped with a servo motor, keep the release bay locked until activated. This allows payload release, after which a spring mechanism closes the bay. Extensive flight testing with strong wind and bearing payloads confirmed good performance, with a 38 minutes autonomy and great robustness, testing the limits by intentionally performing various hard landings, stall tests, and up to 4G maneuvers. P8-NB8 autopilot has been developed entirely from scratch by our team over the past years. The system was used for the first time in last year's competition with optimal results despite the strong wind. It is implemented on MATLAB Simulink and installed on the onboard computer in C++. The autopilot manages the control surfaces through adapted non-linear PID controllers, whose action is based on sensors measurements filtered by a custom extended Kalman filter. The UAV pulsing heart is our in-house developed onboard computer. It's based on a custom PCB that manages the power supply of the OBC, the antennas and all the servos, and holds the communication between the sensors and a Teensy 4.1 microcontroller that runs the autopilot itself and an Arduino Micro that carries some additional computations by some sensors and sends them to the autopilot itself. The avionics sensors include an Xsense MTI 680G AHRS or Attitude, a barometric altimeter, one pitot, an RTK U-Blocks F9P GPS, a leader altimeter, and a current sensor for accurately estimate the main motor and avionic battery's state of charge. As every other part of our UAV, the electronics is designed to be fully modular and compact, ensuring fast and straightforward maintenance. Flight management system includes 5 flight modes. Among these, the vector guidance is the primary testing mode used to tune the control loops. The waypoint navigation mode is based on an advanced trajectory generation and path following algorithm. It generates an optimal trajectory taking into account aircraft performances and geofence limits, updating the flight path in real time in case of obstacles detection. The autopilot is also able to perform the automatic takeoff and landing phases. Furthermore, waypoint navigation has been integrated with other modes required in critical conditions, like return to land and flight termination. The activation logic of these modes is signal and battery dependent. Once engaged, the RTL mode leads the drone to the selected position, then switches to automatic or manual landing. The flight termination mode forces the aircraft in the following setup: throttle closed, full up elevator, full right rudder, full right aileron. Tuning. Numerous modifications have been made to make the aircraft's control system more robust, accurate and reactive than last year. To tune and safely test the autopilot control loops and modes, a parallel Simulink model dedicated to the software-in-the-loop simulation was developed. It is a complete digital twin of the aircraft that allows the simulation of sensors outputs, including noise, the rotation of the aerodynamic control surfaces, and dynamic behavior of the UAV. It exploits a sophisticated mathematical model of the aircraft obtained through Athena Vortex Lattice software and validated with several flight tests. The flight control system tuning has been validated through vectorial guidance data obtained through test flights and simulations. In addition, software-in-the-loop simulations of waypoint navigation have been run to tune the navigation parameters in order to improve the accuracy when reaching waypoints. Real-life testing of the autopilot was conducted by performing waypoint navigations. Missions were planned from ground control stations, streaming the desired waypoint to the onboard computer. These tests have shown that the plane is capable of following an articulated trajectory within a 95% confidence interval of a width of 15.6 feet on every waypoint.
Starting from this year, the integration of a long-steady obstacle avoidance system has begun. The developed system generates an optimal trajectory, taking into account a number of parameters such as the aircraft performance and static and dynamic obstacles. It adapts the flight path in real time to perform obstacle avoidance. In order to avoid collision with other UAVs, obstacle detection is realized through a ZX mini stereo camera connected to the Datsun AGX with a field of view of 82 degrees in front of the aircraft. This allows the identification of long-range objects larger than 15 centimeters with accurate depth perception at high FPS. Thanks to the ROS framework that runs on the Datsun, the stereo camera is capable of generating a high-frequency point cloud through which it is possible to determine the presence of dynamic obstacles and their positions. Once individuated an object in flight, a custom algorithm written in Simulink and C computes an alternative path generating 2 new intermediary waypoints, sent through the OBC using Ethernet protocol. The autopilot then performs an evasive maneuver updating its flight path. After software-in-the-loop simulating tuning, we are able to optimize the maneuver and achieving good stability. We attempted 9 obstacle avoidance maneuvers in many conditions during flights by positioning a slow-motion quadricopter in front of the aircraft path, simulating a competition scenario. In all of them, the aircraft was able to avoid collision by staying at a minimum distance of 15 feet from the UAV. In case of a potential collision with other UAV approaching from a direction other than the front of the plane, the safety pilot is always ready to steer the aircraft away from dangerous situations.
The possibility of using Pixel Keyboard and Autopilot as an alternative to the Teams one was considered and tested. Despite the convenience of a commercial autopilot, a custom one tailored specifically for P8-NB8 assures high versatility in accordance with aircraft's performance and mission requirements, allowing at the same time possible software expansions in the future. Furthermore, its extreme modularity makes repair cheaper. Beyond the valuable learning experience for our students, this project could serve as a springboard for future development of our system, potentially leading to commercial production. Regarding the UAV design choice, a multi-rotor configuration was taken into consideration and tested due to its capability of delivering payload while hovering. However, we ultimately chose a fixed-wing design because of its several advantages, including longer range, faster travel times, and increased loading capabilities. These advantages make it easier to meet mission time constraints and open doors for future development of long-range air delivery capabilities, similar to those employed by many air delivery companies. We opted to discard the use of a 2-axis gimbal after testing revealed minimal impact of airplane roll on photo distortion, motion blur, and captured area, allowing us to reduce weight and to simplify geolocation by exploiting the more precise attitude data from the aircraft's AHRS. Regarding the airdrop system, we explored various concepts, ultimately selecting a delayed parachute airdrop system. The precision of a passive approach of a normal parachute was found to be strongly susceptible to wind gusts, not guaranteeing a stable drop location precision. We divided risks in 4 different categories based on the phase of the year: development, manufacturing, test phase, and competition. Development. To minimize the complexity of such a project, we worked on a comprehensive management plan that outlines clear milestones, identifies potential delays, and outlines contingency plans to mitigate them. We also implemented a robust plan to ensure timely acquisition of all necessary materials. The entire project is in fact focused on modularity on many different levels to ensure great flexibility and reduce costs. Moreover, having 2 similar aircrafts as a backup this year allowed us to maximize testing campaigns of the various departments and stress test all components. Manufacturing. To minimize or eliminate risks for team members and vehicle components, several safety measures have been put in place, and all team members have been provided with safety courses and equipment to minimize injuries during manufacturing processes and tests. Test phase and competition. In addition to the software safety layer measures and switches, the safety pilot is able to completely override all the avionics in case of failure by simply triggering a switch directly on the radio controller, establishing a direct management of the aircraft control surfaces. This is possible thanks to a multiplexer powered by a secondary smaller battery that acts as a hardware switch. Using the experience gained during last year's competition, we worked on the optimization of time and resources spent at the flight line during setup time. It took several trials at our local airfield to fine-tune a strategy by giving each of the 8 members a specific task, simulating competition scenarios and timing our improvement. The defined strategy consists of a short initial debriefing with all the team coordinated by the team captain. The team will then work in parallel. 2 members help the GCS operator by dictating and double-checking the typed waypoint coordinates given by the judges. Another person is responsible for mounting the payload onto the payload mechanism and place them inside of the fuselage. The safety pilot inspects the functionalities of each part of the aircraft by scrolling a checklist with another member. 2 other ODLC specialists are also working on pushing the acquired airdrop information by connecting via wireless communication to the Jetson. The team captain is responsible for timing, coordinating, and ensuring that all operations are carried out correctly. He also provides assistance to struggling departments if needed and mediates with the judges. We plan to use 0 additional operators, since we are confident we have achieved great autonomous performances in all tasks, and that our mission simulations improved from time to time with reassuring total score considering the regulations. Here it is, our proof of flight showing the capabilities of our aircraft. Manual takeoff. Manual flight. Reaching 1,000 feet from safety pilot as shown in the telemetry. Manual landing. Manual takeoff. Getting over 200 feet and transitioning to autonomous waypoint flight. Transition to manual and landing approach. For the last demonstration, a manual takeoff and then transition to autonomous flight for more than 5 miles. The aircraft is capable of getting all the waypoints with a precision of approximately 15 feet. returning to manual for landing. The aircraft has flown for more than 5 miles fully loaded as required by the rules and landed in a 100 feet runway with more than 50% battery remaining. Despite the numerous software-hardware integration problems faced during the years, 2 major crashes that led to 2 aircraft's destruction and the team's limited experience in ODLC systems integration, we managed to attend Suas competition in 2023 as the only team with a custom autopilot. Furthermore, thanks to the consciousness built in the last year and a half that allowed huge improvements in the aircraft's structure, autopilot and ODLC and airdrop systems, we are ready to take part in this year's edition and we feel confident to improve our score.